Hi everyone, so we're going to continue now talking about light waves. In the previous video I just mentioned what the different components of a wave, and in a light wave what we see as the color of the light is really corresponding to the wavelength of that light wave. So as you can see in this example, the red light has a longer wavelength than the blue light, and then what we see as the brightness of the light corresponds to the amplitude of that light wave. Now light is actually best understood if it's modeled as what we refer to as an electromagnetic wave. And really, you don't really need to know more beyond that. The fact that basically, if you have a beam of light going from this direction to that direction, here's the source and it's going to this direction, the best way to predict how that light is going to interact with its surroundings, with other matter, is to model the light mathematically as a combination of two types of wave, which is an electric wave and a magnetic wave. Okay, and this is something that if you want to know the details of, you need to take a physics class, because they're actually going to go through the equations that allows you to again make predictions of how that light wave is going to interact with their surrounding. Now I mentioned before that, now I just mentioned the set of equations that you're going to learn in the physics class. Now the equations that you'll learn, some of them are presented here, and this is what we refer to as Maxwell's equation. I put in capital letters here, do not memorize, because I don't want you to know anything about this. This is really not required for this class. I'm just showing you, and you'll see this again later on where we're talking about wave functions. I just want to show you that everything that we talked about in this topic really has very strong mathematical support behind it. There's a lot of equations and strong theories that kind of back up the discussion that we have. But as I mentioned in the intro video to this topic, in fact it's very hard to understand it if you don't understand the math, and that's why unfortunately with the class requirement that we have, we don't require for this class for you to have calculus as a background, or even any math, advanced math. So as a result, we can't discuss the math, but you can still appreciate hopefully the findings of quantum mechanics. But this is what we refer to as Maxwell's equation, and Maxwell's equation is basically a set of equations that allow you to make predictions of behavior of waves. And light waves, because it's part of it's also a wave, you can use Maxwell's equation to make calculations about the property of light. Okay, now going back to our original idea in classical versus quantum mechanics. In classical mechanics, like I said, you have these two sets of equations: particle equations, which is given by Newton, and then wave equations, which is given by Maxwell. And so we just, what I just showed you is that set of Maxwell's equation that people use to explain the behavior of waves. Okay, now the equation that I do want you to memorize and understand is this relationship between the speed of a wave to its frequency and wavelength. So remember I said before that wavelength is represented by this Greek letter lambda, which is shown right here, and then frequency is represented by the Greek letter nu, okay, which is written very much similar to a lowercase v, and the product of these two yields the speed of light. So if you think about wavelength, the unit of wavelength is the unit of length, which is meter, so some kind of multiple of meter, maybe a prefix in front of it. So if we're talking about visible light, for example, we're usually talking about nanometers is the length. And then frequency is expressed as per second. The unit itself is per second, which really stands for cycle per second. So if you multiply these two, you get meter on one side and per second on the other side. So you get meters per second, which of course becomes the unit of speed, because speed is distance over time. So the speed of light in a vacuum is given this value, 3 × 10⁸ meter per second. If the light is traveling in air, it's going to have interaction with some of the gas particles in air, so the speed is going to be slowed down a little bit. And the speed of light really depends on the the medium that it travels in, and it has to do with something called the refractive index of that medium. We're not going to get into that detail at this point, not in this class, but you just suffices to know for you that the speed of light in a vacuum is 3 times 10 to the 8 meter per second, and that's a constant. It doesn't change. Okay. Now, what I want to do in the next, several slides is basically talk about some of the properties of light, particularly, and there are many, many properties of light, but I'm going to talk specifically about some properties of light that will matter to us in our discussion of quantum mechanics. So the first one I want to talk about is just the fact that if you have a prism, a glass prism, you can basically take white light and then separate it into its component waves. It turns out that white light is not just one wavelength, but it actually is composed of many, many different wavelengths, which can be separated into these different components. And that, of course, is what we call a rainbow. So when you see a rainbow for example, it just rains, you have sunlight coming through. Basically, what serves as the prism here, right, is your rainwater. Okay, so your rainwater, your moisture serves as a prism to bend the light. So what happens is the white light goes in, the light gets bent, and depending on the wavelength, the amount of bending changes. So as a result, you can see from this particular picture that the purple light gets bent the most, and then the red light gets bent the least. And as a result, from the other side of the prism, then you see this rainbow of color. So that's exactly what happens when you see a rainbow as well in real life. Okay, so that's one property of light. So we know now that light is really composed of many, many different ways. Like sunlight or white light is really composed of many, many different light waves, because remember that the color of light corresponds to light waves. So when we see a particular color of an object, let's say this red shirt right here, what's going on is really that we have white light that hits the object, the material in this case, that makes up the shirt. And basically what happens is everything, all the different light components is absorbed by the material, and the one that's reflected is what we see as the color of the object. So in this case, you can explain this color by saying that the white light strikes the shirt material absorbs everything except the red component, the red part of the spectrum of the light spectrum, and as a result that red color is what we see as the color of the shirt. That's the same for all the other types of color we see for objects as well. So I just used this word spectrum, so I want to mention it right here. It turns out that this visible light, which is the light that we can see with our eyes, with human eyes, comprises a very small portion of the entire spectrum of light that's possible. So in fact, you can go, here's wavelength, here's the axis and wavelength, right? So visible light is actually right in this region right here, which is between about 400 nanometers to about 700 nanometers. That's kind of about the cutoff of visible light. But you can see that you can actually have light waves way from very long wavelengths, up to the 100,000, 10,000 meters wavelength, which is the region for our AM, FM radio and television waves, cell phone waves, and so on, all the way to very short wavelengths, 10 to the minus 15, which is that's the region of X-ray and gamma ray waves. Okay, so all of these are actually light. They're all light waves. All of these radio, microwave, infrared, gamma rays, all of them are what we call light. Of course, when we're talking about everyday life, a lot of times we're referring to light really as the visible portion of the light spectrum, but you can have light from all the way from very long wavelength to very short wavelength. Now remember what I said before, wavelength and frequency are inversely related, right? Remember this equation here? They have an inverse relationship. So the longer the wavelength, the shorter the frequency in order for us to get the same speed of light. So as a result, if you look here, the shortest wavelength, which is like the gamma rays, for example, has the largest frequency, and the longest wavelength has the lowest frequency, okay, in terms of relative numbers comparison. So that's really what the electromagnetic spectrum is. What I want you to know out of this is just, understanding the visible spectrum, knowing where the cutoff is, and again, it's 400 for the violet end of the spectrum, and 700 or 750 in this case for the red end of the spectrum. And then you want to know what immediately neighbors these guys as well, the infrared and the ultraviolet, and just kind of have an understanding, have an idea of how it goes from the long end of the wavelength to the short end of the wavelength. Okay, now in the next video I'll talk, if before I move on to the next video, let me just kind of mention this idea that when you look at, you can basically use any of these waves to look at an object. Okay, so usually when we talk about looking at something, we're talking about using visible light, right? Because that's what our eyes have evolved to be able to see. It's under visible light. But you can actually make instruments that can see an object at various, various light waves. So here's actually a great example of how we see the moon. So this is what we see the moon as in visible light at nighttime. If we see the moon, it will look something like this. Now here's all these other pictures are showing how that same moon is observed under all other light wave type. Okay, so if you look at that same moon under ultraviolet, you actually see this picture instead. Okay, now you can see that it's still fairly similar. The light, the visible and the ultraviolet. The ultraviolet doesn't necessarily give you additional information here. It looks pretty similar. But look, if you see the moon under infrared, you see pretty different, a slightly different picture. Now it seems like there's certain parts of it that's really bright, and there's certain parts that's not. And infrared, usually has to do with heat. So basically what this is telling us is that certain parts of the moon is hotter than other parts of the moon that's colder. Okay, if you look at it under microwave, you get a completely different view again of the moon. And then when you look at radio waves, again, very different view, right, of the moon. Same moon that we're looking at under visible. And if you look at X-ray, look at this, it's even different, more different than all the other ones. Okay, so that's kind of the lesson here, is that when we're talking about using light to look at something, in everyday life, we're really just talking about visible light. But in various applications, you can look at that same object with different kinds of light waves. Ultraviolet, microwave, X-ray, and so on.